Hello, my name's Chris Kurzik, and I'm the Principal Engineer at Athabasca Engineering Solutions, AES for short. And what does AES do? Well, first of all, we provide third-party value evaluations. We provide training and certification. We provide equipment re-rating.
We're going to be working on episode 10 or part 2 of Section 8 Division 2. And in this presentation, we're going to talk about exemptions of materials and product specifications. We talk about MDMT curves. Then we're going to talk about the stress ratio adjustment, sometimes also called the coincident ratio. And then the other MDMT reduction options that are available. And with Section 8 Division 2, there are more options available than the Division 1. So let's continue with Section 3.11.2. And more specifically, the minimum thickness and lowest MDMT per section 3.11.2.3 Part E. So it says no impact testing is required if you're under 2.5 millimeters thick, which is similar to what you have in Division 1. The second one is you're limited to an MDMT minus 48 or minus 55 degrees Fahrenheit. And this is identical to Section 8 Division 1 UCS 66D. It's just worded a little bit differently, but it's the same. So let's go to pipe sizes of vessel components 3.11.2.3E. So if we're less than 4-inch in pipe size, okay, then no impact testing is required, but that's limited to 104 degrees centigrade, which is minus 155. So that's the lower wall, the lower limit, excuse me. And the thickness limits are based upon, the yield strength of the material. And so, it's not like, so basically if you have a yield strength between 20 and 35 KSI, then you're exempted up to 1/4 inch in thickness. And if your yield strength is between 36 and 45, then you're exempt to 1/8 of an inch. And you can see how as your yield strength increases, your exemption, you're allowable for your plate before you have to get the exemption drops, right? And if your yield strength is greater than 315, then you're basically sitting at 0.1 inches. Okay, and this is for non post-well heat treat and post-well heat treat P1 materials. And that's refer to UCS 66D because these are essentially identical. So let's look at 3.11.2.4a impact testing exemptions, and let's continue. So ferritic forgings produced to these essential elements is if you have a forging that's a B16.5 flange, or if it's 24-inch and larger, right? Large flanges, you can use a B16.4.7. That applies to Series A and B flanges. Or if you have forged nozzles like integral type nozzles, and then it can apply for the exemption. Okay, so for an as forged condition, which means it hasn't undergone any subsequent heat treating, it's just been forged and then slowly cooled, you get automatically your MDMT is down to minus 18 degrees centigrade or 0 Fahrenheit, and that's without that's the basic exemption. So if you do heat treating and you can show that it's done to a fine grained practice, and we talked earlier about SA20, which means it's heat treated and normalized and tempered or quenched and tempered processes, then your MDMT, you get an instant credit for till minus 29 degrees centigrade or minus 20. And this is identical to Section 8, Division 1, UCS 66C. So 11.24b, materials impact tested in accordance with specifications can receive an exemption. Okay, just like Division 1. And examples could be SA 333 or SA 350. You have to go to the subclasses to get the exact MDMTs, but those would be that. So another thing that's available is the allowable tolerances is minus 3 degrees or 5 degrees Fahrenheit colder than the published value. So you can take advantage of the tolerances to get another few degrees, and that's just because of the error in the data that's provided, and that provides maybe gives you what you need if you're very close. And this is all identical to Section 8, Division 1, UCS 66G. Now we're going to continue on to governing thickness, which is 311.23b, 2 and 3. This is for, now we're going into non-welded castings. Okay, so we always use the largest nominal thickness, and for bolted flanges and flat heads or tube sheets, the larger, okay, of B or above the flat components, and you basically divide it by 4. This, or for dished heads, then you use, this equation. You can take the flathead assembly thickness and divide by 4, or you take the minimum thickness of the dished head part. And now we're going to continue onwards to step 4, which is determine the stress ratio. So we're going to talk about the ratios are based on the main component. So we have a number of different options. You can use the relationship of the required thickness, which is based upon the pressure of the component, the required stress, and then over the it's available. So if you have a very small ratio, that means the part hasn't been stressed very much, and there's room, you can get some credit to reduce your MDMT. And that one there is the thickness basis type of equation. The second equation is called the stress basis, and this is where you calculate the stresses. And but it's the same kind of idea. So it's the available or the required stress over the available stress. And the third one is a pressure temperature basis. And there's some criteria which we talked about earlier in slides, where we talked about the pressure temperature must be used in certain cases. So we're going to move on to exemptions to on the design stress values. We're looking at flanges. So the MDMT is determined by the neck or flange, which is attached, okay? And the bolt-up condition is not considered in the MDMT evaluation. In step 4, which is part D, they talk about the primary tensile strength components, which includes flathead, covers, tube sheets. And we are only allowed to use the temperature basis ratio, which remember we showed 3 of them. The but basically you use 311 to 5A for that relationship. And as we continue on, the longitudinal tensile stresses from bending, they need to include wind, earthquake loads, and vertical loads, not just the longitudinal tensile stresses from bending. And they need to include those external factors in the evaluation of MDMT. And you need to, when you look at, for example, you have a horizontal vessel sitting on two saddles, then you would take the mid-plane bending stress. So let's look at now step 5, determine the final value of the MDMT and evaluate the results. So step 5, we're going to evaluate the results. So let's look at the low stress ratio. So for class 1 materials, okay, or sorry, class 1 design, where there's two classes of materials or designs, and so the safety factor or the design factor for class 1 is higher than class 2. But if the ratio is equal to or less than 3, then the MDMT is 104 degrees centigrade. Likewise, if the ratio is equal to or less than 0.24, then the MDMT is 104. So you can see that there's a difference between if you're going to do a class 1 and a class 2 design. You need to look to make sure that you're using the right tables. Now, there's a figure 312 is for non-post-weld heat treated, and figure 313 is for post-weld heat treated. Now, there's also, the metric version, which is figure 312 with an M on it, and the same with 13, it would be 13M. And there's also tables available for more accurate calculation. Let's take a look at figure 312, and in this case we're looking at the metric version. So along the bottom we're looking at the temperature reduction expressed in degrees centigrade, and along the side here we've got the different the yield strengths across here, which is shown here and here. And then you can see the classes 1 and 2, and you can see that you're required to be less stressed with the class 2 parts, because you're pushing that part closer and closer to the yield strength. There's less of a design factor in for a class 2 material than is a class 1. And again, I've made a video about the differences between the class 1 and class 2 for the allowable stresses for the materials. And so that should sort of explain that. Now, the other one is the one that's subject to post-weld heat treat, and it's also for non-welded parts, like shown, here. And then of course over here is for not subject to post-weld heat treatment over here. So we're going to go on to a bit more detail. So if the yield strength is greater than 450 megapascals or 65 ksi, for post-weld heat treatment, you can use this following equation. It's quite an involved equation. I believe there is examples that you can ASME has, so you can test your formula to make sure it's accurate. But you can basically use the temperature reduction here, and you can calculate it quite accurately using this rather elaborate equation. And bear in mind that this is in degrees in Fahrenheit and KSI, and this particular equation. So be aware of the units. And that's equation 3.4, by the way. So we're going to continue here. Determine the final value of MDMT. Evaluate the results. So let's continue. So we have a final adjustment to the MDMT. We have to use that equation 3.5. And then just like in division 1, we basically take, the stress found from the governing equation, and then we take our stress ratio, which we determine the temperature reduction, and then basically we move forward with that. And that's equation 3.5. So 3.11 to 5a reminds the designer that every part in, say, a pressure vessel or a pressure containing equipment has to be analyzed on a case-by-case basis to determine what each one is, and then putting them all together and finding the warmest component, and then that's how we determine our final MDMT for the assembly, which would go eventually onto the nameplate. So the establishment of MDMT can be used for fracture mechanics, which is unique to Division 1. If you can look up 3.11.2.8. ASME has a very good example in I believe it's one of the PTB editions, and it's 3. I believe there's an example, and we may in the future go through this example in detail. And basically, it invokes API 579.1, also called ASME FFS Part 9, and these two are basically merged together. And we have a number of videos on this topic as well. We plan to do more in the future. And basically, they require a Part 2 or Part 3 fracture mechanics assessment, and that can be used to determine the MDMT. So in this case, you're basically using inspection data, and you're looking for flaws, and you're determining, based upon the flaws, what your MDMT is capable of. So in case you need to derate it or whatever, this is typically used for existing vessels and equipment. So the stresses are also can be used from thermal stresses from heat treating and thermal loading. You can use this for those kind of applications as well. This kind of criteria. And you can look at flaw size evaluation as well. And there's a Charpy energy correlation that can be found to assist with the evaluation, and it's found in Appendix F or F4. And I believe it's pre-2012 edition that can assist you with determining the required Charpy energy factors. Let's look at 3.11.2.9, post-weld heat treatment at low temperatures. So welded joints are required to be post-weld heat treated if the MDMT is less than 48 degrees Fahrenheit, and we have a class ratio of class 1 with the stress ratio is greater than 0.3. And in the other cases, class 2, the ratio is 0.24. So there are exceptions for type B1 or type 1A and B joints, they must be 100% RT'd, and it does not include cone to cylinder joints. So there's special requirements for the type of configuration. And the maximum transition slope, for unequal thickness is limited to 3.1. And the part 2 of B says it's required for only lightly loaded attachments. And the maximum fillet size is limited to 10 millimeters or 3/8 of an inch. And, we talked about lightly loaded components. They define that as less than 25% of the allowable stress. One other thing is LP or MPI per part 7 is required. So there's a lot of exceptions here, for post-well in service at low temperatures.
I hope that you found this presentation useful and valuable to you. This was provided by Athabasca Engineering Solutions. We'd love to hear your feedback and your thoughts on further videos. And we'd love to hear from you. Maybe we can do some business. Please subscribe to our channel so you don't miss a thing. Take care for now.